Hello Sleepy Science subscribers. Welcome back to the channel. Thank you for being here tonight. Before we begin, please remember to subscribe and leave a like so that more people can drift into calm sleep with us. I also have a small request to make this space feel even more connected. I am truly curious about where you are watching from and what time it is for you right now. So feel free to float into the comments and let me know. Your messages soften the atmosphere here and help us build a quiet horizon together. Now, let us gently move into today's story under the dim light of the universe. Imagine yourself drifting through a quiet horizon where the universe glows under dim light, a cosmic space so still that time itself feels slowed. Stars appear as distant sparks and vast clouds of dust float gently through the darkness. In this serenity, you sense the presence of something invisible yet everywhere, something that fills space the way water fills an ocean. This is the Higgs Field, an energy field spread across the entire universe, present in every direction, in every atom, in every breath you take. To understand it more clearly, imagine the universe shortly after the Big Bang. Everything was hot and chaotic, particles rushing in all directions with no mass, moving at the speed of light. But as the universe cooled, a field emerged, spreading through space like a soft mist. This field did not shine or vibrate like light. Instead, it settled quietly across the cosmos. Particles drifting through this field began to slow, their movement resisting the smooth flow of the field. The more strongly a particle interacted with this field, the heavier it became. Picture yourself floating between these early particles. Some glide through easily, barely touching the field, moving light and free. Others push through it slowly as if wading through invisible molasses. This difference is what we call mass. A particle that interacts more with the Higgs field becomes heavier, while a particle that interacts less remains lighter. It is not weight in the usual sense, but a deeper resistance to acceleration shaped by the invisible presence of the field. Now imagine the Higgs field as an endless ocean of calm energy. Gentle waves drift through it at all times, carrying small vibrations. One of these vibrations is the Higgs boson, a tiny ripple in the field discovered in 2012. The boson is not the field itself, but a brief disturbance in it, like a droplet rising from a vast sea. Its discovery confirmed that the field exists and that it plays a crucial role in giving structure to the universe. As you drift deeper into this idea, imagine the Higgs field touching every particle in your body. Electrons, quarks, and other tiny building blocks float through this field with resistance that defines their mass. Without this field, atoms could not form, stars could not shine, galaxies could not gather, and the quiet horizon of the night sky would be empty. The Higgs field softens the chaotic dance of particles, turning motion into structure, forming a universe capable of building itself layer by layer. Let your breath slow as you imagine the Higgs field surrounding everything, like dim light spreading across cosmic waters. Feel the deeper calm that comes from knowing that an invisible presence shapes the universe quietly, steadily, without noise or force. As you drift deeper into the quiet mystery of the Higgs field, imagine the universe around you settling into an even softer stillness. The quiet horizon stretches across a cosmic canvas washed in dim light, and you float slowly through it as gentle waves of silence move through the dark. Your thoughts soften, and your breathing steadies, guiding you toward deeper calm as the Higgs field reveals more of its hidden nature. Though invisible and silent, this field shapes everything in the universe, determining how matter forms and how energy transforms into structure. To understand this more clearly, imagine the Higgs field not as a force, but as a smooth background that fills all of space. Unlike gravity and electromagnetism, the Higgs field does not push or pull. Instead, particles drift through it, and the way they interact with this field determines how much mass they have. Some particles glide through effortlessly, like light floating across a calm sea. Others move more slowly, feeling a subtle resistance as if wading through soft currents. This resistance is what gives them mass equality that defines how easily they accelerate, how strongly they respond to forces, and how they build the material world. Now imagine the early universe again, but from a slightly different perspective. As the cosmos cooled, the Higgs field settled into a stable state, forming a kind of cosmic backdrop. Before this transition, particles had no mass. They moved freely at the speed of light. But when the field took shape, it altered the rules of the universe. It was as though a vast ocean appeared where there had previously been empty air. The particles that once drifted unimpeded now floated through this ocean, some feeling only slight effects while others slowed dramatically. This slowing transformed energy into matter, allowing complex structures to form. Picture the Higgs field as a smooth landscape stretching beneath the quiet horizon. Gentle waves ripple across it, though most remain too faint to notice. Once in a while, a larger ripple appears. This is the Higgs boson, the particle excitation of the field. It is not the field itself, but a brief expression of its presence, a momentary vibration rising from the stillness. When scientists detected the Higgs boson in 2012, it was like seeing a tiny splash and realizing it came from an entire invisible ocean beneath reality. To visualize how mass arises, imagine pushing your hand through water under dim light. The water offers resistance not because it pushes you back, but because it exists everywhere around you. In the same way, particles receive mass, not because of a force acting on them, but because of how the Higgs field surrounds them. The more strongly a particle couples to the field, the more resistance it feels, the heavier it becomes. Light particles float with ease, while heavy particles drift slowly as if moving through a cosmic fog. As you float through this idea, let your thoughts soften into the awareness that mass is not an inherent property, but a relationship between a particle and the Higgs field. Without this field, electrons would race at light speed, failing to orbit atoms. Quarks would never bind into protons and neutrons. The universe would expand as a thin, diffuse mist, unable to form stars, galaxies, or life. The Higgs field stabilizes everything, creating a foundation upon which matter can rest and evolve. Now imagine the Higgs field stretching infinitely across the universe, blending into the fabric of space itself. It does not shimmer or hum, yet its influence is everywhere. Its existence turns pure energy into structure, shaping the balance between motion and rest. As you drift through this thought, gentle waves of understanding ripple through your awareness, bringing deeper calm and a sense of connection to the hidden architecture of the cosmos. As you drift further into the quiet landscape of the Higgs field, imagine the universe dimming into an even softer glow. The quiet horizon stretches into a calm expanse where dim light drifts like a thin veil over cosmic dust. You float gently through this silence, and gentle waves move through your awareness, softening each thought and guiding you into deeper calm. In this softened stillness, the deeper workings of the Higgs mechanism begin to reveal themselves, showing how particles gain their mass through interactions woven into the very fabric of the field. To understand this more fully, imagine the Higgs field as a smooth energy surface spread throughout the universe. This surface has a peculiar shape, often compared to a valley surrounding a low ring. Before the universe cooled, the Higgs field rested at the center of the valley where symmetry was perfect and particles had no mass. But as the cosmos expanded and temperatures dropped, the field shifted into the lower ring around the valley. This shift is called spontaneous symmetry breaking, and it marked the moment when mass became possible. Now, imagine yourself floating inside this valley-shaped field. At the center, everything feels weightless, drifting without resistance. But when the field moves outward into the ring, a new environment appears. In this new region, particles begin to interact with the field, and these interactions determine their mass. Some particles couple strongly to the field, feeling a heavy drag as they move. Others couple only lightly, floating effortlessly. This coupling is not a push or a pull, but a deep relationship between the structure of the field and the nature of the particle itself. The Higgs mechanism explains this interaction at a deeper level. Particles that carry weak force charges connect directly to the Higgs field. When the field settled into its new configuration, it altered the behavior of the weak force carriers. Two of these particles gained mass, becoming the W and Z bosons. They drift slowly, compared to the massless photon, which does not interact with the Higgs field, and therefore floats freely at the speed of light. This difference explains why electromagnetism behaves over long distances, while the weak force fades quickly, barely reaching beyond the nucleus of an atom. Imagine these bosons drifting through the field. The photon floats effortlessly through space, unaffected by the Higgs field. The W and Z bosons, however, move as though surrounded by a dense fog, feeling the field's resistance with every step. This resistance is their mass. Without it, the weak force would stretch across the universe in the same way light does. Instead, it remains short-ranged shaping processes such as nuclear decay, while leaving everyday life untouched. Now let your thoughts drift outward again. Picture a quiet horizon where the Higgs field spreads like a calm ocean beneath dim light. Every particle you have ever known floats within this ocean, interacting with it in its own unique way. These interactions soften the motion of some particles, slowing them into heavier forms, while letting others drift freely. This delicate arrangement gives rise to the complexity of matter, creating atoms, molecules, and the structures that fill the universe. In the absence of the Higgs field, everything would move at the speed of light. There would be no solid surfaces, no weight, no orbiting electrons, no formation of elements. The universe would be a bright fog expanding endlessly without structure. The Higgs field brings deeper calm to this chaos, arranging motion into order, shaping the dance of energy into forms that last. As you breathe slowly, imagine yourself floating through this invisible field, feeling its quiet presence surrounding you. It does not glow or vibrate under dim light, yet it holds you and every particle around you in a soft embrace. The Higgs field whispers the rules of mass through gentle waves that drift across the cosmos, giving shape to everything that exists. As you drift deeper into the quiet mystery of the Higgs field, imagine the universe settling into an even more tranquil glow. The quiet horizon stretches outward beneath dim light, and you float gently through this softness as gentle waves ripple through your awareness. Each breath helps your thoughts soften, guiding you toward deeper calm, as we explore how the Higgs boson reveals the hidden structure of the field that fills all of space. To understand this more clearly, imagine the Higgs field as a calm ocean spread across the entire universe. For most of cosmic history, this ocean remained invisible, its presence known only through the way it shaped the motion of particles. But hidden within this ocean lies a vibration, a tiny ripple that rises for only the briefest moment. This ripple is the Higgs boson, the particle discovered at CERN in 2012, and its existence serves as the first direct confirmation that the field itself is real. Now imagine shrinking down into this vast ocean of energy. You float above the surface where gentle waves sway under dim light. Suddenly, a small disturbance appears, traveling across the field like a single drop hitting still water. This disturbance is a Higgs boson. It does not travel far, and it does not last long, but its presence reveals that the field can vibrate. Just as a ripple in water can tell you the water exists, the Higgs boson tells physicists the Higgs field surrounds everything. From a scientific viewpoint, this vibration carries mass and energy, and it interacts with other particles in predictable ways. When the Higgs boson forms, it briefly separates itself from the field, becoming a particle that scientists can detect. But its lifespan is incredibly short. It decays almost instantly into other particles that drift outward through detectors, leaving faint traces behind them. These traces act like footprints, confirming that something passed through the field with enough energy to shake it. The discovery of the Higgs boson was a monumental moment, because it confirmed a theory that explained how particles gain mass. Without this ripple, the entire structure of particle physics would collapse. The standard model relies on the Higgs mechanism to unify the weak and electromagnetic forces and to describe how particles float between states of motion and rest. The boson's existence softens the gap between theory and reality, proving that the invisible field truly fills the universe. Now imagine drifting outward from this microscopic world into the vastness of cosmic space. Picture the Higgs field stretching across the quiet horizon like a soft mist. Under dim light, galaxies float like lanterns, drifting slowly in the darkness. Everything from the largest cluster of stars to the smallest electron carries the imprint of the Higgs field. Without this field, galaxies would never form and stars would never shine. The universe would remain a thin, bright fog instead of the structured cosmos we see today. Consider the role of the Higgs boson in this grand structure. Though tiny and fleeting, its vibration hints at something profound. It reveals that the field is not static, but dynamic, capable of gentle waves that drift through space-time. These vibrations are rare, requiring enormous amounts of energy to create. Yet each ripple tells the same quiet truth. The universe is filled with a field that shapes its form, guiding particles into patterns that allow atoms and stars to exist. As you breathe slowly, imagine resting beside this invisible ocean. You feel the presence of the field, not through sight but through understanding. It softens the movement of some particles, allowing them to become heavy. It lets others float freely. Its influence drifts through every corner of reality, shaping the quiet rhythm of matter itself. In the dim light of this thought, you feel deeper calm, knowing that you are held within a field that touches every particle in your body. As you drift deeper into the quiet story of the Higgs field, imagine the early universe glowing under a dim light, as if wrapped in a cosmic veil. The quiet horizon stretches across newborn space, and gentle waves of heat ripple through the expanding cosmos. You float through this ancient moment, and your thoughts soften as the universe begins to cool, guiding you toward deeper calm, while revealing how the Higgs field shaped the evolution of everything that would one day exist. In the first instant, after the Big Bang, the universe was a furnace of energy particles rushing in every direction with unimaginable speed. There was no structure, no mass, no atoms, only a brilliant storm of pure motion. But as the universe expanded, it began to drift toward cooler states. This cooling allowed the Higgs field to appear, spreading across space like a quiet mist, forming its stable value and settling into the energy minimum of its unique potential. Imagine floating through this moment as the universe transitions from chaos into order. Before the Higgs field formed, particles behaved like weightless sparks drifting freely through the hot plasma. Photons, neutrinos, and other particles all moved at the speed of light, floating without resistance. But when the Higgs field settled into place, everything changed. The particles, interacting strongly with the field, slowed. They gained mass. They became the building blocks of matter. This shift was as profound as turning sound into music or dust into planets. To visualize this transition, imagine a wide cosmic plane under dim light. At first, the plane is perfectly flat and smooth, offering no resistance to anything that crosses it. But slowly, the plane transforms into a gentle landscape with a valley shape. The Higgs field occupies this valley, filling the universe with its stable presence. Particles that drift across this landscape feel its texture. Their motion softens as they interact with the field. Light particles float lightly across the surface. Heavy particles press deeply into the valley, moving more slowly. This moment of symmetry breaking marked the dividing line between a universe filled with pure energy and one capable of forming structure. Once particles obtained mass, they could gather. They could attract. They could slow long enough to form atoms. Without the Higgs field, electrons would never orbit protons. Quarks would never bind together. Stars would never ignite. Galaxies would never swirl across the quiet horizon. The universe would remain a thin, drifting glow instead of the rich cosmic tapestry we witness today. As the cosmos continued to expand and cool, the Higgs field kept its stable value, holding the rules of mass in place. Imagine this field stretching endlessly through space like a calm ocean beneath dim light. Gentle waves drift slowly across it, but the overall level remains steady, ensuring that the masses of particles do not change. This constancy allows chemistry to remain the same in every corner of the universe. A hydrogen atom in a distant galaxy behaves just like one on Earth because the Higgs field is equally present everywhere. Now imagine yourself resting within this early universe, floating in the soft glow of forming structure. You feel the Higgs field surrounding you, touching every particle with its quiet influence. The field does not push or pull. It simply exists, offering resistance that shapes motion. In this subtle presence lies the foundation of all complexity. Every breath you take, every star you see, every atom in your body owes its existence to this silent field, drifting through space-time. As you drift further into the quiet understanding of the Higgs field, imagine the modern universe spread wide beneath a calm sky filled with stars. The quiet horizon glows under dim light, and galaxies float like lanterns, drifting slowly across the dark. Gentle waves of calm expand through your thoughts, softening your awareness as we explore how the Higgs field influences particle behavior today. Though invisible and silent, it continues to shape every moment of the universe with steady and unwavering presence. To begin, imagine every particle you know drifting through the Higgs field as it moves. Electrons do not simply glide freely. They interact with the field, feeling a soft resistance that slows their motion, giving them mass. Quarks feel even more of this resistance, making them heavier. Photons, however, float effortlessly through the field, never slowing, never bending. They do not interact with the Higgs field at all, which is why light travels at the highest possible speed. This contrast reveals the deep connection between mass and motion, and how the Higgs field quietly defines the identity of each particle. Now, picture a proton beneath dim light. Inside it are quarks held together by the strong nuclear force. Yet the mass of the proton is not just the mass of these quarks. A large part arises from the energy of motion inside the proton, energy shaped by the Higgs field, giving mass to the quarks themselves. As the proton floats through space, the Higgs field surrounds it, influencing its properties without ever needing to change or reveal itself. Mass becomes not a fixed quantity, but a relationship determined by the strength of a particle's interaction with the field. Imagine drifting deeper into quantum space, where particles blink into and out of existence as virtual excitations. These fleeting particles also feel the Higgs field. Even in their short lifetimes, they interact with the field, gaining temporary mass. This interaction shapes the quantum foam that lies beneath everything, smoothing the chaotic dance of creation and annihilation. The field softens the extremes of quantum fluctuations, bringing deeper calm to the microscopic structure of the universe. From the scientific perspective, this universal presence means the Higgs field permeates every corner of space, no matter how empty it appears. Even in the vast darkness between galaxies, the field remains steady. Its value does not fade with distance or change from one region to another. Because of this, atoms forming in distant galaxies behave the same as atoms forming here. Chemistry follows the same rules across the entire universe. This uniformity is not guaranteed by any law of symmetry, but by the quiet stability of the Higgs field drifting through all of space-time. Now allow your thoughts to float to a particle accelerator, where scientists create high-energy collisions under dim light. When particles smash together at enormous speeds, they disturb the Higgs field for the briefest moment. These disturbances create Higgs bosons, which decay almost instantly into lighter particles. By studying these decay patterns, physicists can understand how strongly different particles interact with the Higgs field. The deeper the interaction, the heavier the particle. These measurements confirm the quiet influence of the field, without ever letting us see it directly. Imagine yourself floating beside one of these microscopic collisions. You sense the sudden ripple, a Higgs boson rising from the stillness of the field. It lasts for only a moment, then dissolves into fragments that drift outward like gentle waves spreading through the detector. This ripple reveals the field's presence, its energy, its structure. Though the boson vanishes almost instantly, the information it carries lingers, guiding physicists toward a deeper understanding of how the universe grants mass. You feel the Higgs field around you even now, though it cannot be seen. It fills every inch of space, stretching across the quiet horizon with calm and constant influence. Light floats freely. Matter drifts slowly. Energy softens into structure. And the silent architecture of mass remains stable across billions of years, shaped by this invisible ocean, spread evenly across the cosmos. Across the universe, a quiet background of energy stretches from one edge of the cosmos to the other, a calm and steady presence known as the Higgs Field. It does not flicker or shine, yet its influence is everywhere. Under dim light scattered across distant galaxies, this field allows particles to drift between states of motion and rest. The galaxies that float through cosmic darkness move as they do because the Higgs field defines the mass of every constituent particle within them. Without this silent framework, the universe would have no weight, no structure, only motion without form. Modern physics describes this field as a constant value, permeating all of space, a uniform backdrop that never fluctuates at large scales. When particles move through this background, they experience a type of resistance. Not friction, not pressure, but a fundamental coupling determined by their identity. Quarks couple strongly, electrons less so, and photons not at all. Their differing responses to the field explain why some particles glide quickly, while others drift slowly. This quiet distinction echoes through the entire structure of matter. Inside atoms, the influence of the Higgs field becomes even more striking. Electrons orbit nuclei because they possess mass, and that mass arises from their interaction with the field. If this interaction were weaker, electrons would float away too easily, never settling into stable orbits. If it were stronger, atoms would collapse inward. The field softens extreme possibilities, creating a balance that allows atoms to remain calm and steady across billions of years. The quiet horizon of chemistry, biology, and the structure of life is built upon this subtle interaction. In the world of high-energy physics, the Higgs field reveals itself through the brief appearance of the Higgs boson. When protons collide at extreme speeds, the smooth symmetry of the field is disturbed. A pulse rises, lasting only a fraction of a second. This pulse decays immediately, scattering into lighter particles that drift outward in delicate trajectories. These fragments carry information about the coupling between matter and the field. Each pattern maps the strength of this interaction, confirming that the Higgs field shapes mass through its constant presence. The field also influences forces. The weak nuclear force is short-ranged because its carriers, the W and Z bosons, interact strongly with the Higgs field and therefore carry significant mass. Their mass limits how far the weak force can travel. Meanwhile, the photon passes through the field untouched, carrying no mass, allowing electromagnetism to float freely across the universe. This contrast shows how the field determines the reach of fundamental interactions, shaping the quiet architecture of forces beneath dim light. Even in the vacuum of space, the Higgs field remains active. Virtual particles rise and fade within it, traces of quantum fluctuations that never fully disappear. The field governs their mass as well, steadying the fluctuations and bringing deeper calm to the restless quantum foam. In this way, the Higgs field acts as a soft anchor, preventing the microscopic world from dissolving into chaotic motion. Every galaxy, every star, every atom follows the gentle rules set by the Higgs field. Its presence shapes the weight of planets, the brightness of stars, and the stability of molecules. It does not change with time. It just does not need attention. It drifts quietly through space-time, carrying the same constant value everywhere. The calm uniformity of the cosmos rests upon this silent field, a foundation written into the deepest layers of reality. Across the vast structure of the universe, the Higgs field acts as a quiet and steady background shaping the behavior of particles, without ever revealing itself directly. Its presence can be understood through the simple idea that motion changes depending on how strongly a particle couples to this field. When a particle interacts intensely, its movement slows, as if drifting through a dense medium. When the interaction is weak, its motion remains light and free, allowing it to float easily across space. These differences determine everything from the formation of atoms to the life cycle of stars under the dim light of distant galaxies. In particle physics, this interaction is encoded mathematically in what is called the Yukawa coupling. Each particle has its own coupling strength to the Higgs field, and this strength sets its mass. The top quark, for example, couples very strongly and thus carries a large mass. Electrons couple more softly and therefore remain much lighter. Neutrinos couple only faintly, drifting almost effortlessly through the universe. Photons do not couple at all and retain their massless nature. This hierarchy defines the architecture of matter as clearly as gravity defines planetary motion. The Higgs field does more than give mass to isolated particles. It stabilizes the vacuum of the universe, ensuring that the laws of physics remain calm and consistent. If the strength of the field or its potential had been slightly different, the vacuum could have been unstable, leading to abrupt shifts in the properties of particles. Instead, the field settled into a gentle minimum that persists across cosmic history. This stable configuration stretches across the quiet horizon from galaxy to galaxy, allowing chemistry and astrophysics to unfold with predictability. In accelerator experiments, the Higgs boson continues to illuminate how the field interacts with other particles. The boson decays quickly into combinations of photons, Z bosons, bottom quarks, or tau leptons. By measuring the frequency of these decays, physicists infer the strength of each coupling. These measurements confirm that the Higgs field softens the difference between energy and mass, transforming pure motion into rest. Each decay channel paints a piece of the larger picture, showing how deeply the field is woven into the structure of reality. Beyond the standard model, physicists explore theoretical extensions to understand whether the Higgs field is alone or part of something larger. Some theories propose additional Higgs fields or heavier cousins of the Higgs boson. Others suggest that the field may drift slowly over cosmic time, altering its value in subtle ways. If this drift exists, it would influence the masses of particles and possibly the expansion of the universe. Yet observations show remarkable stability. The calm value of the Higgs field appears constant across billions of years, bringing deeper calm to cosmic evolution. Cosmology also raises the question of whether the Higgs field contributed to the early inflationary expansion of the universe. Under certain conditions, its potential could have driven rapid expansion, smoothing the cosmos. While this idea remains speculative, the shape of the Higgs potential influences how the universe transitioned from high-energy states to the gentle waves of structure that formed later. The link between cosmology and particle physics hints at a deeper unity, suggesting that the field may have played a role far beyond giving mass alone. Within stars, the Higgs field determines the properties of the particles involved in fusion. Proton mass, electron mass, and neutrino behavior all depend on the field's constant presence. Slight changes in these values would prevent stars from igniting, or would cause them to burn too quickly. The steady glow of stellar light beneath dim light, scattered through the galaxy, relies on the field's precise tuning. Life emerges only because the field's influence remains balanced and unwavering. The Higgs field touches every aspect of matter, yet leaves no visible trace. It shapes the world indirectly, allowing reality to drift into stable patterns rather than dissolving into pure energy. Its constant background allows particles to float with defined identities and interactions. Layer by layer, the field softens the extremes of the quantum world, creating an orderly and predictable universe. In the deeper layers of particle physics, the Higgs field plays a quiet but essential role in determining how forces behave. The Standard Model connects particles and interactions through a network of symmetries, and the Higgs field breaks one of these symmetries in a very specific way. Before this symmetry-breaking photons, W bosons and Z bosons were indistinguishable within the equations of the early universe. They existed as blended components of the same unified interaction. Once the Higgs field settled into its stable value, the symmetry softened and separated, giving mass only to the W and Z bosons. Photons remained massless and continued to float unhindered across the universe. This separation explains one of the most important differences in physics. Electromagnetism can drift across vast distances because its carrier, the photon, has no mass. The weak nuclear force fades quickly because its carriers are heavy. This split shapes how stars synthesize elements, how radioactive decay unfolds, and how energy moves within the heart of atoms. In dim light, scattered across galaxies, the balance between these forces writes the script of cosmic evolution, all steered quietly by the Higgs field. The field also influences exotic states of matter that appear in extreme environments. In neutron stars, for example, particles are squeezed so tightly that their interactions with the Higgs field shift slightly. The altered conditions may modify the effective mass of quarks and leptons, though only by subtle margins. Yet even small variations can change the behavior of dense matter, determining whether it drifts smoothly or collapses into more exotic phases. These environments allow physicists to explore how deeply the Higgs field is woven into the fabric of reality. In the early universe, the Higgs field transitioned from a high-energy state into its current stable configuration. This process likely produced gentle waves of energy that drifted through the primordial plasma data. Some theories propose that these waves could have left imprints on cosmic structures, faint echoes still floating through the universe today. In this sense, the Higgs field does not merely give mass. It participates in the unfolding story of cosmic formation, its influence stretching from the smallest particle to the quiet horizon of the observable universe. Quantum field theory describes the Higgs field using a potential shaped like a valley, with the field resting at the lowest point of that valley. Tiny fluctuations around this resting point generate the Higgs boson. These fluctuations behave like small vibrations in a calm sea, rising briefly before fading into deeper calm. Because the boson is heavy, its creation requires immense energy, which is why only particle accelerators can produce it. Nevertheless, every time a boson forms and decays, it offers another glimpse into the hidden geometry of the field. The longevity and stability of the Higgs field raise deeper philosophical questions about the universe. If the field had settled into a slightly different value, the masses of particles would change dramatically. Stars might never ignite. Atoms might never form. The universe might drift into a cold and featureless void. The stability of the field suggests that our cosmic environment is finely tuned in ways that continue to inspire speculation. Whether this fine-tuning emerges from deeper physical principles or simply reflects the conditions necessary for observers to exist remains unknown. In theoretical physics, supersymmetry once offered a natural explanation for the stability of the Higgs field. Predicted partner particles that would soften quantum fluctuations and prevent the field from drifting into unstable values. However, these partners have not been observed, leaving the question open. Other theories, such as multiverse models or additional Higgs fields, attempt to address the mystery, but none have been confirmed. The quiet consistency of the Higgs field remains one of the most intriguing aspects of modern physics. Across the cosmos, the Higgs field continues to float as a silent background, shaping mass, governing forces, and guiding the formation of galaxies. It leaves no mark on the sky, yet its influence stretches across every star and every atom. Beneath dim light, scattered across the universe, the field keeps reality steady, offering gentle waves of stability that drift through space-time and allow the universe to settle into deeper calm. The Higgs field continues to shape the universe in ways that extend far beyond the masses of elementary particles. Its constant value underpins the balance between energy and form, allowing matter to structure itself without collapsing into chaos. In the emptiest regions of space, where galaxies appear only as faint smudges under dim light, the Higgs field remains unchanged. This uniformity ensures that physical laws do not drift from one region to another, but instead remain steady across the quiet horizon of the cosmos. One of the subtle influences of the Higgs field lies in the Yukawa interactions within the Standard Model. These interactions mathematically encode how strongly each particle couples to the field and determine the mass hierarchy of the universe. Some particles, like the top quark, exhibit an intense coupling that grants them significant mass. Others, like the electron, interact more softly, drifting through the field with only mild resistance. This hierarchy shapes atomic structure because heavier particles remain bound tightly while lighter ones float more freely. Without this balance, atoms would never reach stable configurations. In composite particles such as protons and neutrons, the story becomes more intricate. Their overall mass arises mostly from the energy stored within their internal motion and from the strong nuclear force binding their quarks. However, the Higgs field still plays a crucial role. It sets the baseline mass of the quarks themselves, stabilizing the building blocks that ultimately determine the mass of larger structures. Even the faintest particle interactions soften into order because of this field's quiet influence. The field also plays a part in the evolution of the early universe. When it transitioned from a high-energy state into its stable configuration, a small but crucial amount of energy was released. This energy helped the universe settle into calm expansion. If the Higgs field's potential had been slightly different, the transition could have unfolded violently, possibly preventing galaxies from forming. Instead, the shift created gentle waves of energy that drifted through the young cosmos, allowing matter to clump into stars and stars to cluster into galaxies. Modern cosmology recognizes that the Higgs field may be connected in deeper ways to dark energy, the mysterious force accelerating the expansion of the universe. Some theories propose that subtle interactions between the Higgs field and the vacuum energy could influence cosmic acceleration. Others suggest that variations in the field's value might float beneath the surface of space-time, creating effects too faint to detect with current technology. These ideas remain speculative, but they reflect the ongoing search for connections between the particle world and the vast cosmic landscape. In extreme environments such as black hole surroundings, the Higgs field might behave in unusual ways. Near the intense curvature of space-time, quantum fields can shift in response to gravitational energy. Although the Higgs field remains stable on large scales, theoretical work suggests that its value could drift near singularities. Such changes would affect particle masses, altering the behavior of matter as it approaches the event horizon. These possibilities hint at a deeper conversation between gravity and the Higgs mechanism, two frameworks not yet unified in a single theory. High-energy collisions in particle accelerators continue to refine our understanding. By studying the Higgs boson's decays, physicists measure how precisely the particle matches predictions. So far, the results float remarkably close to the Standard Model expectations. These confirmations deepen the mystery because they reinforce that the Higgs field is exactly as stable as equations demand, while offering no explanation for why it takes this particular form. Each experiment softens the boundary between known physics and deeper questions still unanswered. Across billions of light years, the Higgs field remains quiet and constant, forming the foundation upon which matter assembles itself. The galaxies drifting across cosmic darkness do so because the field grants mass to their stars and planets. The atoms forming the dust between those stars remain stable because the field holds their structure. In every direction, from the brightest nebula to the dimmest void, The Higgs field floats as a silent architect, shaping the ways particles move and how the universe settles into deeper calm. The Higgs field influences the universe not only by granting mass, but also by shaping how particles decay and transform. Particle decay is a fundamental process, a slow rearrangement of energy that occurs in even the quietest corners of space. The rate at which certain particles decay is tied directly to their mass, and that mass comes from the Higgs field. A heavier particle decays more quickly because it carries more internal energy. A lighter particle lingers longer. This delicate timing governs the life cycles of unstable matter drifting through cosmic environments under dim light. The muon is a clear example. Heavier than the electron, it decays rapidly into an electron and neutrinos. Its short lifetime is a direct consequence of its mass, which originates from its interaction with the Higgs field. Tau particles decay even faster, their heavy mass accelerating the process. Quarks follow similar rules. Their differing masses determine which decays are allowed and how quickly they occur. Behind each of these events lies the silent influence of the Higgs field, shaping the tempo of matter's transformations across the quiet horizon of the cosmos. In high-energy, astrophysical events such as supernova explosions, the Higgs field continues its quiet work. As massive stars collapse and explode, extreme temperatures tear particles apart. In these states, the influence of the Higgs field becomes more apparent because particles behave differently under such intense conditions. The masses granted by the field determine which reactions occur and which particles float freely in the explosion's debris. Even in the chaos of a dying star, the Higgs field maintains order by regulating the motion of matter. The role of the Higgs field extends to neutrinos as well, though their mass arises indirectly. Neutrinos interact so faintly with the Higgs field that their masses remain incredibly small, allowing them to drift across the universe with almost no obstruction. This near weightlessness enables them to float through entire planets without slowing. Their behavior has shaped the early universe by influencing how matter clustered after the Big Bang. Tiny variations in their mass created gentle waves in the distribution of galaxies, leaving signatures that cosmologists still study today. Some theories propose that the Higgs field itself may not remain constant forever. Over unimaginable timescales, the field could drift toward a new configuration. If this occurs, particle masses would shift, and the universe might transition into a different phase. Current measurements suggest the Higgs field sits in what is called a metastable vacuum. It is stable for now, but could theoretically soften into a lower energy state in the distant future. If such a shift happens slowly, the universe would float through a calm transformation. If it happened suddenly, the change would ripple across reality with dramatic consequences. Yet, the timescales involved are so vast that the universe may fade into deeper calm long before any such transition takes place. Quantum corrections also influence the Higgs field. Particles constantly interact with the field through virtual processes that drift in and out of existence. These interactions slightly modify the field's value, creating a delicate balance between competing effects. Supersymmetry once provided an elegant solution by pairing each particle with a heavier partner that would offset these quantum corrections. Without evidence of these partners, the stability of the Higgs field becomes a deeper question, one that continues to soften the boundary between theoretical physics and the still unknown. What remains certain is that the Higgs field shapes every form of matter from the smallest particle to the largest cosmic structure. Galaxies float through the universe with mass determined by the field. Atoms remain stable because electrons have mass. Stars burn calmly because quarks carry specific values shaped by this invisible background. The Higgs field drifts through all of space, quietly determining how matter moves and how the universe holds itself together. The Higgs field also shapes how particles combine to form larger structures, influencing everything from atomic nuclei to the chemistry that unfolds across galaxies. At the smallest scales, The masses of quarks determine how strongly they bind together inside protons and neutrons. Because the Higgs field sets these masses, it indirectly oversees the stability of nuclei. A slightly different field strength would alter the balance of forces inside the nucleus. Protons might drift apart too easily or bind too tightly, leaving no room for complex atoms. Instead, the field maintains a balanced environment where matter can float into organized forms. As atoms form, the mass of the electron becomes crucial. Electrons orbit nuclei because their mass allows them to settle into quantized energy levels. If electrons were much lighter, they would drift too freely to bind reliably. If they were much heavier, they would collapse inward, softening the delicate structures that make chemistry possible. The Higgs field fixes the electron mass at a precise value. This precision determines the shapes of molecules, the behavior of stars, and the pathways through which life emerges beneath dim light scattered across the universe. In the interstellar medium, where gas and dust drift between stars, the Higgs field ensures that hydrogen and helium behave consistently across cosmic time. Clouds collapse under gravity, forming new stars because their atoms have predictable masses. These clouds float across the quiet horizon, forming patterns that guide the birth of entire star systems. Had the Higgs field been even slightly different, the thermal behavior of these clouds would shift dramatically. Some would never collapse, while others might collapse too rapidly for new stars to stabilize. On planetary scales, the Higgs field shapes the density of matter, which in turn determines how planets form. Rocky planets require elements like oxygen, silicon, iron, and carbon. These elements arise through nuclear fusion in stars, a process governed by the masses of protons and neutrons. The Higgs field sets these masses, and therefore sets the stage for planetary architecture. The gentle waves of fusion inside stars depend on this precise mass balance. If the field were different, planets might form as gas giants only, or perhaps not at all. The Higgs field even influences the internal dynamics of stars. In stellar cores where temperatures and pressures soar, the mass of particles determines reaction chains that fuel a star's glow. The proton-proton chain, the CNO cycle, and supernova reactions all depend on particle properties shaped by the field. A slight shift would soften or enhance fusion conditions, altering the brightness and lifespan of stars. The calm glow under dim light seen in distant galaxies is a direct consequence of the Higgs field holding these processes in balance. The Higgs field also affects cosmological evolution on grand scales. The mass distribution of matter influences how galaxies drift through space, forming clusters and filaments. Simulations show that slight differences in particle masses produce dramatically different cosmic structures. Because the Higgs field defines these masses, the shape of the cosmic web reflects its influence. The sprawling patterns of galaxies floating across billions of light years are a quiet imprint of the field's steady presence. On quantum scales, the Higgs field acts as part of a larger tapestry of fields, each with its own energy and behavior. These fields interact in subtle ways that remain poorly understood. Quantum fluctuations ripple through them in gentle waves, shaping probabilities and transitions. The Higgs field softens some of these fluctuations by giving particles mass, thereby taming the restless motion of the quantum vacuum. In this sense, the field brings deeper calm to the foundation of physical law, preventing the universe from drifting into instability. Even the passage of time becomes meaningful, because particles with mass can move slower than light, allowing clocks to tick and processes to unfold in sequence. Without the Higgs field, time itself would lose structure because everything would travel at the same speed. The quiet rhythm of cause and effect across the universe depends on the mass that the Higgs field provides. The Higgs field also plays a crucial role in determining how symmetry appears and disappears in the universe. At high energies, such as those in the earliest moments after the Big Bang, Physical laws carried a remarkable degree of symmetry. Forces that now seem distinct were interwoven, sharing a unified structure. As the universe expanded and cooled, this symmetry softened and separated. The Higgs field was responsible for triggering this transition, breaking the symmetry in a controlled way so that particles could drift into new identities and form the foundation of modern physics. The mechanism behind this transition begins with the shape of the Higgs potential. At extreme energies, the field sat near the center of a symmetrical state where its value was zero. As temperatures dropped, the potential changed shape and the field settled into a new equilibrium. This shift was not violent but steady, like gentle waves drifting across a calm sea. As the field stabilized, it created a distinct ground state that endowed particles with mass. The quiet horizon of the universe changed permanently, allowing complexity to emerge from what had once been an energetic uniformity. This breaking of symmetry did not just produce mass. It determined how particles interact. The weak and electromagnetic forces, once unified, became different because the Higgs field separated their carriers and assigned mass selectively. The photon remained massless and continues to float across the universe without slowing. The W and Z bosons became massive and now drift only short distances before decaying. This split shaped the behavior of atoms, stars, and everything built from them. A universe without this transition would drift endlessly as a featureless fog beneath dim light. Some aspects of the Higgs field's behavior raise deep theoretical questions. One of these concerns the stability of the vacuum. Calculations suggest the Higgs field may rest in a metastable state, not the absolute lowest energy configuration. This means that the field could, in principle, drift into a different state given enough time or under extreme conditions. Such a shift would change fundamental constants and rearrange the fabric of physics. Yet, this possibility exists on such immense timescales that the universe may fade into deeper calm long before any transition occurs. For now, the field remains steady, maintaining the balance that allows matter to exist. The Higgs field also interacts subtly with gravity. Although this relationship is not yet fully understood, changes in the field's value would influence space-time curvature. The masses of particles determine how strongly they bend space-time, so altering the Higgs field would adjust gravitational dynamics across the cosmic web. Whether this interplay hints at a deeper unifying principle remains one of the open questions at the intersection of quantum physics and cosmology. In models of inflation, the rapid expansion of the early universe, the Higgs field may have played a part in smoothing the cosmos. While the dominant driver of inflation is thought to be another field, the Higgs field could have interacted with it, helping to soften variations and bring gentle order to the early plasma. These interactions, though faint, may have left traces still drifting across the cosmic microwave background as tiny ripples in temperature and density. On more speculative fronts, some theories propose that the Higgs field might influence dark matter. If dark matter particles couple faintly to the Higgs field, their masses would arise in a similar way to ordinary matter. This coupling would be subtle, allowing dark matter to float through galaxies with minimal interaction, yet still providing enough mass to shape cosmic structures. Detecting such interactions remains an ongoing challenge, but the possibility suggests that the Higgs field touches even the invisible components of the universe. Across these scales, the Higgs field remains a silent architect. It shapes symmetry, mass, and the quiet evolution of physical law. It stretches from the smallest particles to the outermost galaxy clusters, drifting across the universe with unwavering strength. Beneath dim light scattered across space, the field maintains balance, softens extremes, and ensures that the cosmos rests in deeper calm. The Higgs field also shapes how temperature and density influence the behavior of matter across the universe. At extremely high temperatures, such as those created in particle accelerators or those present in the first fractions of a second after the Big Bang, the interaction between particles and the Higgs field weakens. In these conditions, particles begin to drift more freely, behaving as if their masses are reduced. This transition hints at a universe where mass is not a fixed property, but a relationship that softens under extreme energy. As the temperature decreases, the coupling strengthens again, restoring the familiar structure of matter under the quiet horizon of lower energy physics. In heavy ion collisions, scientists briefly recreate these high-energy conditions. Nuclei collide at nearly the speed of light, creating a quark-gluon plasma, a state where quarks float without the usual confinement inside protons and neutrons. In this plasma, the Higgs field's influence is muted, and particles behave differently from the way they do in ordinary matter. Studying this state offers insights into how the early universe evolved, drifting from a hot and fluid medium into a structured cosmos built on stable masses defined by the Higgs field. When the universe cooled during its first microsecond, the Higgs field gradually settled into its present configuration. This process, often described as a phase transition, unfolded with care. The field shifted from a symmetric state to a broken symmetry state where its value became non-zero. This shift determined the masses of particles and set the stage for nucleosynthesis, the formation of the first atomic nuclei. Gentle waves of cooling allowed the field to stabilize smoothly, so that the particles emerging from the early plasma could combine in predictable ways. As the cosmos expanded further, larger structures began to form. Dark matter and ordinary matter drifted together into clusters that seeded galaxies. These formations depended critically on the masses of particles, meaning the Higgs field's steady value indirectly shaped the large-scale architecture of the universe. If the field had drifted even slightly during this period, the growth of galaxies could have stalled or accelerated beyond stability. Instead, a calm and controlled evolution unfolded beneath dim light stretching across deep space. The Higgs field also contributes to the energy stored in empty space. This vacuum energy interacts with gravity and plays a role in the expansion of the universe. Although this contribution is small compared to the observed acceleration caused by dark energy, the interplay between the Higgs field and the vacuum remains one of the deepest puzzles in physics. It raises questions about why the vacuum energy does not soar to enormous values, given the presence of quantum fields like the Higgs. The gentle calm of cosmic expansion suggests that some unknown mechanism softens these contributions, keeping the universe from tearing itself apart. Another intriguing aspect involves the renormalization of the Higgs field. Quantum fluctuations constantly nudge the field's value through virtual processes. These fluctuations do not destabilize the field thanks to a delicate balance between competing effects. The fact that this balance holds across immense energies and timescales indicates a hidden order within quantum physics. The Higgs field floats in this quantum environment without drifting away from its stable value, revealing a calmness at the heart of otherwise turbulent interactions. The field also influences matter under extreme pressures. In the dense cores of neutron stars, where particles pack together with tremendous force, the effective interactions between quarks and the Higgs field may shift. These shifts could subtly alter the behavior of matter, creating exotic states, such as quark matter or hyperon-rich phases. Understanding these phases helps scientists piece together how the Higgs field behaves under conditions far beyond Earth's experience. Even in such extreme realms, the field maintains a role in determining how matter responds and how forces soften or intensify. Across all these phenomena, the Higgs field remains a silent yet constant participant. It determines how matter behaves at temperatures from near absolute zero to the highest energies achievable in nature. It shapes quantum interactions and cosmic evolution alike. Under the dim light of distant stars, its influence continues without wavering, guiding the universe toward deeper calm as particles drift along the rules set by this quiet and ever-present field. The Higgs field also shapes how particles move through space when they approach the limits of known physics. As particles gain enormous energy and accelerators, their behavior begins to drift toward the conditions of the early universe. Their effective masses soften slightly because high-energy motion reduces the influence of the Higgs coupling. This effect is subtle but measurable, and it reveals how mass is not a rigid property, but a dynamic relationship governed by energy and field interactions. Under dim light and vast accelerators, beams of particles float through magnetic curves, their motion guided by both momentum and their quiet connection to the Higgs field. Inside protons and neutrons, the Higgs field determines the masses of the constituent quarks, but not the entirety of the nucleon mass. Most of the mass arises from the kinetic energy of quarks and gluons confined within the strong nuclear force. Yet, without the Higgs field supplying a baseline mass to these quarks, the dance inside a nucleon would change dramatically. The balance between confinement and motion would shift, altering how nucleons combine and how the atomic world forms. In this sense, the Higgs field provides the quiet horizon upon which nuclear structure rests. This influence extends into atomic and molecular behavior. The mass of the electron determines the size of orbitals, and therefore the geometry of molecules. Slight shifts in electron mass would distort chemical bonds, changing the structure of water, carbon compounds, and every molecule essential to life. Because the Higgs field fixes the electron mass with remarkable precision, these molecular structures remain stable across billions of years. The gentle waves of chemistry flow smoothly because the field maintains consistency in the properties of matter. In condensed matter physics, the Higgs mechanism appears in unexpected ways. Superconductors, for example, exhibit a phenomenon analogous to the Higgs effect. When electrons pair into Cooper pairs and move without resistance, the electromagnetic field acquires an effective mass inside the material, causing magnetic fields to drift away rather than penetrate deeply. This similarity does not mean superconductors contain the Higgs boson, but it shows how certain ideas echo across different branches of physics. Under the dim light of a laboratory, the equations describing superconductors float alongside those describing the Higgs field, in particle physics offering deeper calm through mathematical unity. The Higgs field may also play a role in the early universe's energy balance. As it transitioned into its stable state, the field released energy, contributing to cosmic heating in that era. This energy faded as the universe expanded, but the transition helped set the conditions for later structure formation. The timing of this shift influenced how quarks combined into hadrons and how light elements formed during nucleosynthesis. Each stage flowed into the next, like gentle waves shaping the emerging cosmos. Some models propose that the Higgs field might interact faintly with fields beyond the standard model. Dark matter, for example, could couple weakly to the Higgs field, gaining mass in a manner similar to ordinary particles, but floating through galaxies almost undisturbed. If true, this interaction would help explain the mass of dark matter without requiring additional complex mechanisms. Experiments continue to search for evidence of such couplings by studying Higgs boson decays with increasing precision. The Higgs field may even influence the long-term fate of the universe. If the vacuum is metastable, as some calculations suggest, then the field could drift toward a different configuration in the far future. This shift would alter particle masses and reshape physical laws. However, the likelihood of such a transition occurring in any foreseeable timescale is extremely small. The universe appears to rest comfortably within the current Higgs field configuration, drifting slowly toward deeper calm as cosmic expansion continues. In all these realms, the Higgs field acts with quiet constancy. It governs the mass of particles, shapes the structures they form, and influences the interplay between energy and matter. Across the quiet horizon of the universe, its presence softens extremes and steadies the motion of everything that exists. Beneath dim light scattered across cosmic space, particles float according to the rules written by this silent and enduring field. The Higgs field reaches into the deepest layers of particle identity by shaping how fundamental fermions obtain their distinct masses. Each quark and lepton possesses its own coupling to the Higgs field, and these couplings differ by vast amounts. This hierarchy forms the backbone of the Standard Model and determines how matter behaves from the microscopic scale of particle interactions to the macroscopic scale of stellar evolution. The top quark couples so strongly to the Higgs field that it becomes extremely massive, while the up and down quarks couple softly, drifting with much lighter masses. This contrast may appear arbitrary, but it creates stability across the universe and allows matter to float into complex forms. This mass hierarchy also influences flavor physics, the study of how particles transform into one another through weak interactions. During these transformations, the Higgs field determines how often certain transitions occur, because the masses of particles set probabilities for decay channels. Heavy quarks decay more frequently, drifting through short lifetimes, while lighter quarks float through longer periods before transforming. The entire pattern of particle behavior softens into predictable rhythms governed by mass differences, all traced back to the quiet presence of the Higgs field. Inside stars, the Higgs field continues to shape structure. Fusion reactions rely on the precise mass of protons and neutrons, which in turn depend on the masses of their constituent quarks. If the Higgs field assigns slightly different masses, stars might burn far too quickly or fail to ignite at all. The dim light of main sequence stars scattered across the galaxy reflects a balance preserved by the field. This balance ensures that fusion releases energy at a steady rate, allowing stars to drift through billions of years with calm persistence. In white dwarfs and neutron stars, the story becomes more extreme. Here, matter is compressed to extraordinary densities, and the behavior of particles shifts accordingly. Quarks and leptons in these environments still carry masses defined by their Higgs couplings, but their interactions occur under intense pressure. The mass thresholds set by the Higgs field decide which particles remain stable and which transform, influencing the layered structure of compact stars. Even in these harsh environments, the field acts as an underlying guide, shaping how matter responds to gravity's pull. Beyond astrophysics, the Higgs field also influences early structure formation in subtle ways. Tiny fluctuations in temperature and density in the young universe became amplified by gravity. The masses of particles determined how they drifted under these gravitational pulls. Light particles like neutrinos floated more freely and smoothed out small-scale structures, while heavier particles clumped together more strongly. The quiet horizon of cosmic structure depends on this mass balance, and therefore on the Higgs field's steady value. Modern research explores whether the Higgs field might couple to new undiscovered particles. If additional scalar fields exist, the Higgs could mix with them, creating gentle waves of interaction that modify its properties. This mixing might appear in precision measurements as small deviations in the Higgs boson's decay rates, or as rare events in particle collisions. The search for such interactions continues because any sign of deviation would hint at physics beyond the Standard Model, floating just beyond current understanding. The Higgs field may also influence the geometry of spacetime indirectly. Since particle masses determine how strongly they curve spacetime, changes in the field's value would reshape gravitational behavior. Although the field itself does not produce gravity directly, it sets the mass scale for all particles, meaning its constant value is woven into the quiet fabric of general relativity. This connection hints at deeper unity between quantum fields and spacetime, one that remains uncharted yet softly implied by the interplay between mass and gravity. Across the quiet horizon of the universe, the Higgs field remains constant, drifting silently through every cubic centimeter of space. It shapes decay rates, fusion cycles, gravitational structure, and the identities of particles. Beneath dim light from scattered stars, its presence softens the extremes of physics and allows matter to float in stable forms. Through every scale from the quantum to the cosmic, the field holds the universe in deeper calm. The Higgs field also determines how particles behave when they approach relativistic speeds, revealing the quiet interplay between mass and motion. As a particle accelerates toward the speed of light, its energy increases dramatically, yet its mass set by the Higgs field remains constant. This fixed mass establishes a limit that prevents the particle from ever reaching light speed. The photon, which does not couple to the Higgs field, floats effortlessly at that ultimate speed, drifting across the cosmos without resistance. In contrast, electrons and quarks, shaped by their interaction with the field, soften into slower trajectories the more energy they gain. This relationship creates the familiar boundary between matter and light. In quantum electrodynamics, the mass of the electron influences how it interacts with the electromagnetic field. These interactions generate corrections that subtly modify physical quantities like the magnetic moment. The Higgs field, by defining the mass of the electron, sets the scale at which these corrections occur. Without this mass, the electron's behavior would drift into a realm where bound states such as atoms could not form. The calm, predictable structures of chemistry rest on the Higgs field's quiet contribution to quantum interactions. Within the weak force, the Higgs field plays an even more essential role. The weak interaction governs processes like beta decay and neutrino production. The masses of the weak force carriers, the W and Z bosons, arise directly from the Higgs mechanism. Their large masses restrict the range of the weak force, confining it to short distances within atomic nuclei. This limited range softens the influence of weak interactions on everyday matter, allowing stars to burn steadily rather than collapsing into instability. Under dim light scattered across the galaxy, the rhythm of stellar fusion is shaped by the Higgs field's control over these bosons. The Higgs field also influences the stability of matter in ways that reach beyond the standard model. Protons, for instance, appear to be stable over immense time scales, yet theories of grand unification propose that they could eventually decay. The probability of such decay depends on the masses of intermediate particles predicted by these theories. Those masses, in turn, depend on the Higgs field. Even the longevity of protons may be softly linked to the field's quiet configuration drifting beneath every atom. In cosmology, the Higgs field contributes to the energy density of the vacuum. Although the measured vacuum energy is far smaller than theoretical predictions, its existence suggests a delicate cancellation among quantum fields. The Higgs field is one of these contributors. Its constant value supports the cosmic expansion rate, helping maintain a balance that keeps galaxies from drifting apart too quickly or collapsing inward. The quiet horizon of the universe's expansion is shaped partly by the field's steady presence. When scientists model the early universe, they find that small adjustments to the Higgs field's value produce dramatically different outcomes. A slightly larger vacuum expectation value increases particle masses enough to prevent stable hydrogen from forming. A slightly smaller value allows neutrons to remain stable outside nuclei, undermining the creation of heavier elements. The narrow window that allows stars and planets to exist is defined by the Higgs field. This delicate tuning raises questions about deeper principles that might soften the apparent coincidence of such precise conditions. Research continues into whether the Higgs field interacts with fields associated with dark energy or dark matter. If such interactions exist, they may cause subtle variations in the Higgs field across cosmic distances. These variations could leave imprints on the distribution of galaxies or on the pattern of cosmic microwave background fluctuations. For now, observations suggest remarkable uniformity, with the field floating steadily through space, its value unchanged across billions of light years. The Higgs field's influence even reaches into the definition of time itself. Because particles with mass experience time differently from massless particles, the The existence of mass gives structure to the flow of time. Clocks rely on transitions between energy states, transitions that depend on particle masses. Without the Higgs field, these transitions would vanish, and time would lose much of its meaning. The gentle waves of temporal order arise from the quiet architecture shaped by the field. Across all these layers, the Higgs field appears as a silent moderator of physical law. It sets boundaries, guides interactions, and ensures consistency. Beneath dim light scattering through galaxies, it stabilizes matter, allowing the universe to drift through cosmic ages with deeper calm. The Higgs field also shapes how symmetry violations arise in the universe, offering clues to why matter exists at all. In the earliest moments after the Big Bang, matter and antimatter should have been produced in equal quantities. Yet, the observable universe contains far more matter. This imbalance, known as baryon asymmetry, requires subtle violations of symmetry within the fundamental laws of physics. Some of these violations involve the Higgs field and its interactions with heavy particles whose masses depend directly on their coupling to the field. In certain theoretical models, as the universe cooled and the Higgs field settled into its present value, tiny imbalances drifted into the particle interactions, allowing more matter to survive than antimatter. In electroweak baryogenesis scenarios, the Higgs field plays a central role. As the field transitioned from its symmetric state to its non-zero value, the universe may have passed through a phase boundary. The properties of this boundary would determine whether particles reflected differently depending on their matter or antimatter nature. This differential reflection could create a small but crucial excess of matter. Although this remains speculative, it illustrates how the quiet settling of the Higgs field beneath dim light in the early cosmos may have softened the symmetry between matter and antimatter enough to let galaxies form. The Higgs field also interacts with the concept of vacuum energy. Quantum field theory predicts large contributions to the vacuum from all fields including the Higgs. Yet observations show the vacuum energy is extremely small. This enormous discrepancy remains one of the deepest puzzles in physics. If the Higgs field contributed fully as predicted, the universe would have expanded so rapidly that no structure could form. Something must cancel or soften these contributions, allowing the expansion to drift gently rather than explode uncontrollably. Whether this balancing mechanism lies within the Higgs field itself or within deeper layers of physics remains an open question. The field's behavior also plays into the concept of metastability. Current measurements suggest that the Higgs potential may not be absolutely stable, but only metastable. This means the universe rests in a state that is stable for now, but could, in principle, transition to a lower energy state. Such a transition would be catastrophic, altering particle masses and reshaping the laws of physics. The possibility floats on calculations involving the Higgs mass and the top quark mass, both of which influence the curve of the potential. Yet the timescales for any such drift are so vast that the universe is expected to remain in deeper calm for trillions of years. The Higgs field also appears in extensions of the standard model that attempt to unify forces or introduce new particles. In supersymmetric theories, multiple Higgs fields exist, each contributing to mass generation in different ways. These extra fields allow the equations to soften certain divergences that trouble the standard model. Although no supersymmetric particles have been detected, the mathematical structure remains elegant, suggesting that the Higgs mechanism may be part of a larger framework floating beneath known physics. Another extension involves axions, hypothetical particles introduced to solve the strong CP problem. In some models, axions interact faintly with the Higgs field. These interactions would subtly alter the mass landscape and influence how the Higgs boson decays. The search for axions continues because they could also form dark matter, drifting silently through galaxies while interacting only through gravity and possibly through gentle waves of scalar fields. Mixing. If axions exist, the Higgs field may share a quiet connection with the invisible matter shaping the cosmos. Even the stability of atoms owes its nature to the Higgs field. The mass of the neutron is slightly greater than the mass of the proton. This difference allows neutrons outside nuclei to decay and protons to remain stable. The delicate mass balance arises partly from quark masses, which the Higgs field determines. A small shift in the field would soften or invert this mass difference, causing hydrogen to be unstable. Without stable hydrogen, stars would not shine and planets would never float within habitable zones. The quiet horizon of cosmic structure relies on this subtle mass arrangement. Across these complexities, the Higgs field maintains its silent presence. It shapes the symmetry of forces, the existence of matter, and the behavior of stars. Beneath dim light scattered across the universe, it steadies physical law, allowing galaxies to drift across cosmic time with deeper calm. The Higgs field extends its influence into the very definition of what it means for a particle to exist within quantum field theory. In this framework, particles are not tiny solid objects, but excitations that rise from underlying fields. Each type of particle corresponds to a different field, and the Higgs field determines how sharply these excitations form. When a field's excitation carries mass, it must interact with the Higgs field. When it does not, it floats freely without resistance. This distinction shapes the entire architecture of quantum reality, determining which excitations drift slowly and which move with effortless speed beneath the quiet horizon of spacetime. In the standard model, the Higgs field appears as the only fundamental scalar field, meaning it has no direction in space. This lack of direction allows the field to soften symmetries in a unique way. While vector fields such as electromagnetism carry information about direction, the Higgs field influences magnitude. It sets the scale for masses, drifting uniformly across space rather than pointing in any specific direction. This quality allows it to break symmetries without shattering the delicate mathematical structure of the standard model. Renormalization group equations reveal that the Higgs field's behavior changes gently as energies increase. At high energies, the effective strength of the Higgs self-coupling drifts, creating the possibility that the field's stability may shift at scales far beyond current experiments. If the coupling becomes negative at extremely high energies, the vacuum may be metastable. This metastability suggests that the quiet calm we observe today is only one layer of a deeper landscape, a valley among other valleys, where the universe could float if conditions changed. Yet the field remains steady, its current value maintained across billions of years. The Higgs field also interacts with thermal history during cosmic evolution. As the universe cooled below a critical temperature, the field transitioned into a non-zero value, generating masses for particles. This transition was not only a structural change, it altered how sound waves and density fluctuations moved through the primordial plasma. The masses of quarks and electrons influenced how the early universe clumped into pockets that eventually formed galaxies. The gentle waves of these fluctuations drifted outward and left faint imprints in the cosmic microwave background. These imprints confirm that particle masses, set by the Higgs field, shaped the earliest stages of cosmic structure. Within modern particle experiments, the Higgs boson reveals how the field couples to heavy particles. Its decay into bottom quarks, or tau leptons, confirms strong couplings, while rare decays into photons provide insight into quantum loops that include particles like the top quark. Each decay pathway maps the invisible network of interactions. These interactions float like patterns beneath dim light in the data produced by detectors, showing how deeply the Higgs field weaves itself into particle behavior. Wow, the Higgs field may even influence hypothetical particles far heavier than anything currently observed. Many theories propose heavy right-handed neutrinos whose masses arise through interactions with the Higgs field. These neutrinos could drift unnoticed through the early universe, yet decay in ways that create the observed matter-antimatter asymmetry. Their existence would extend the field's influence far beyond the particles present in today's laboratories. If such particles exist, they remain hidden in deeper layers of the cosmos, their footprints softened by time. In gravitational physics, the Higgs field enters subtle territory. While gravity couples to energy and mass, the Higgs field sets the mass scale for nearly all ordinary matter. This indirect relationship connects the field to the structure of space-time itself. If the Higgs field had a different value, the curvature of space-time around stars and planets would shift accordingly. Planets might fail to form stable orbits, or stars might collapse too quickly. The quiet harmony of gravitational dynamics depends on masses shaped by the field. Across all these domains, the Higgs field remains constant, drifting quietly through every region of space. It determines the mass of particles, guides cosmic evolution, stabilizes atoms, and shapes the symmetry of forces. Under dim light scattered across galaxies, particles float according to rules written by the field. Through quantum interactions and cosmic flows, the Higgs field softens extremes and keeps the universe resting in deeper calm. The Higgs field completes its influence by shaping the enduring balance between existence and possibility across the universe. It provides the mass scale that allows particles to drift within stable ranges, ensuring that interactions proceed neither too quickly nor too slowly. Because the field maintains a constant non-zero value, processes such as nuclear fusion, atomic bonding, and chemical reactions occur with gentle regularity. Without this steady value, matter would lose its structure, collapsing into extremes or floating without cohesion beneath the dim light of cosmic emptiness. Instead, the Higgs field softens these extremes and guides physical law toward balance. This balance extends to the formation of galaxies. As matter cooled and clumped after the Big Bang, the masses of particles, set by the Higgs field, determined how gravity shaped large-scale structures. Heavier particles fell more readily into forming halos of dark matter and ordinary matter, while lighter particles floated outward. Over billions of years, these interactions produced spirals, clusters, and filaments that fill the universe. The quiet horizon of cosmic structure owes its shape to the mass landscape sculpted by the Higgs field, a landscape that remains consistent across time. Even the behavior of dark matter may be influenced by the Higgs field. Though dark matter interacts mostly through gravity, some theories propose faint couplings to the Higgs mechanism. Such couplings would grant dark matter particles their mass while allowing them to drift invisibly through galaxies. Experiments attempt to detect rare Higgs decays that might reveal these hidden interactions. If confirmed, the Higgs field would be shown to touch not only visible matter, but also the unseen foundation of cosmic structure. The Higgs field also appears in discussions about the ultimate fate of the universe. If the vacuum is metastable, then the field may one day drift toward a new configuration. This possibility rests on values measured for the Higgs boson and the top quark. Should their precise masses imply metastability, the universe sits in a delicate valley that could, in theory, transition to a deeper one. Such a transition would propagate outward at the speed of light, altering particle masses and reshaping physical law. Though the timescales involved are unimaginably vast, the idea highlights how deeply the field is woven into cosmic destiny, floating silently beneath the surface of reality. In more immediate terms, the Higgs field continues to guide laboratory discoveries. Particle accelerators examine Higgs production and decay with increasing precision, searching for gentle waves of deviation from the standard model. Such deviations might point toward additional fields, hidden symmetries, or new particles. Each measurement refines the picture of how the Higgs field interacts with known matter, mapping its influence across quantum and cosmic scales. Under dim light in detector halls, data streams drift across screens, revealing the quiet fingerprint of the field. The Higgs field's simplicity makes its cosmic influence even more remarkable. It is uniform, constant, and scalar, without direction or orientation. Yet from this simplicity emerges the mass of every known particle. It acts like a calm ocean beneath all other fields, providing a medium through which particles move and acquire weight. Without this ocean, the universe would be filled with particles traveling at the speed of light, unable to settle, unable to combine, unable to form stars or planets. The deeper calm of the universe depends on the Higgs field's steady presence. Across cosmic time, the Higgs field remains unchanged, drifting softly through every region of space. It shapes the smallest structures of matter and the largest patterns of galaxies. It floats beneath all interactions, determining the pace of time, the structure of atoms, and the evolution of stars. The universe rests within this quiet framework, held together by a field that reveals itself only through rare particle excitations. Beneath the dim light of distant galaxies, the Higgs field continues to soften the extremes of physics and guide reality toward gentle balance, allowing the cosmos to drift forever within deeper calm.